Um, okay, thanks, Pasha. So yes, my name is Ken Raffinetti. I am a software developer here at Argonne National Laboratory, and I'm going to talk about kind of the state of the union of MPICH and UCX. So the way we use UCX in the MPICH or MPICH project. So just a little background on MPICH. You know, we're very HPC oriented. You know, we aim to be, you know, the MPI used on lots of large scale clusters. And the way we do that is we kind of develop MPICH here at Argonne, the core open source version of MPICH. And then we rely on many of our partners to kind of pick up the open source version that we produce, extend it, tune it, package it for their specific use cases, their hardware, their software environments, and then you know, then the outer ring here is the applications that sit on top of those derived implementation. So that's kind of the MPICH development and distribution model. So today I'm going to talk about how we're using UCX and MPICH. So we've been using it for quite a while, dating back to, you know, an initial integration, I don't know how many years ago, probably, you know, around the time of the first annual meeting. And then I'll hit on a couple of specific points. You know, there's you know, things that keep coming up with request handling in MPICH that's different than the way requests, MPI requests are handled in OpenMPI, and so how that kind of affects us, and how UCX can support us, which today is much better than it was. How we're using the UCP Active Message API, this optimization we're using for multi-threading called multi-VCI, which I'll explain more later on, and then some things we have slated for work in the future, and a few other odds and ends before we wrap up. So that's what I'll cover here. So again, more background on MPICH. So MPICH, this is kind of a simplified diagram of its structure. So the important thing here is now we're using what we call CH4 as a default device layer implementation. So the CH in MPICH stands for Chameleon, which was a project that dates back, you know, prior to MPI, so over 30 years or so. So Chameleon has evolved over the years. This is the fourth iteration, which started probably about 7 or 8 years ago, maybe a little bit longer. It was kind of a redesign for lower overhead, kind of more capable network APIs like UCX, like libfabric. So you can see UCX kind of sits below the CH4 layer as what we call a net mod or a network module. And essentially UCX, the goal is, you know, the MPI API calls directly down to UCX without doing hardly anything at all. You know, we try to minimize branches, minimize interpretation of arguments until we get to that network module where, you know, in terms of UCX, it can handle a large portion of the MPI API, you know, quote unquote natively. And so there's, you know, a pretty good match between APIs there. And that, but so when we call UCX directly using, you know, using what we can from the MPI API. If there is a bad match, you know, if the call is complex or uses some, you know, however you want to, you know, however complex it gets in MPI, which it can, then we call up into what we call the generic layer. And the generic layer is, you know, basically the MPICH protocol layer where we have a packet, you know, packet header and packet handlers. And this is what we actually use the UCP Active Message API for kind of layering that MPICH protocol over the available UCX transports. So this is the state of support today. So again, we developed the UCX netmod. Primarily, the Argonne MPICH team maintains it at the moment, though we have help from the NVIDIA Mellanox team and had a lot of help in the past on that. So we just released a beta of MPICH 4.0. And so MPICH 4.0 now adds all of the new MPI 4.0 functionality that was just standardized earlier this year. This includes like large count APIs, partition communication, persistent collectives. So all that is there now in MPICH. It's in beta status right now. There's still some bug fixes that need to be applied, but we're hoping to have an RC and a full release out, hopefully end of year. If not, then very early in 2022. So we have included an embedded UCX 1.11.2 in MPICH. So if you are building from source and you select UCX as your configuration and you don't have it installed on your machine, it will build the embedded version. We switched configuration. I think other projects are doing this too. We now prefer the external library if it can be found on the machine. Again, if it's new enough to support some of the features that we require. So I'll talk about some of the changes we made and how we now require newer versions of UCX in order to support them. This version of MPICH has also done a lot in terms of GPU support. So MPICH supports 3 flavors of GPU: NVIDIA, AMD, and Intel GPUs. Though for UCX, we only support the NVIDIA and AMD configurations. So and we have tested with that. We have clusters in-house or machines in-house where we've ran and validated these configurations. So in terms of what's natively supported by UCX in MPICH, again, like I said, so point-to-point is obviously a good match for the tagged interfaces. We've recently upgraded to using the NBX versions of the tagged interfaces, which I'll talk about later. We have contiguous put-get RMA support, depending on your window flavor. So we support this for when-create and when-allocate windows. In MPI RMA. We don't yet have it merged. We want to merge atomic support. It was under development by one of my colleagues here at Argonne, who unfortunately left for a different position. So that still needs to be kind of worked on and merged into the MPICH main branch. But there is a PR. And I think some of the concerns were mainly around UCX versions, which I think we resolved now, so that we might be able to speed up the process of including that fairly soon. Like I said, the generic path, we're now using the CH4 active message, the UCX or UCP active message API, which is a pretty straightforward port. I'll talk about that in a later slide. Something we don't support with UCX is MPI dynamic processes. So it's the support for things like MPI com spawn and connect accept and things like that. We actually have a pull request that looks to add this, though we're running into an issue we had in the past with the size of the worker address. I see that there's a pull request from Mikhail that's looking to address, shrink the size of the worker address. We haven't tested this yet, but it's something I've marked as potential for helping us through this issue. Otherwise, it's probably a PMI. It's a PMI limitation that we could probably work around. We worked around it for address exchange, business card exchange during MPI init. I suppose we can implement a similar workaround for dynamic processes. It would just be nice if we didn't have to. And then I have this box here, just some raw performance numbers. I ran these a while ago, but they still hold fairly true today. Just illustrating that we get nice latency and bandwidth performance kind of out of the box with UCX. It doesn't take a lot of effort to realize how the good performance numbers that are possible using MPICH with UCX. So again, we get good latency and bandwidth. I think this is using the RC transport. This is 2 nodes, 2 InfiniBand nodes in our JLSE system evaluation cluster, one of our evaluation clusters here at Argonne. Let's see. Okay, request handling. So this comes up. This has come up in the past, and it's something that continues to come up. In the integration of UCX and MPICH. So just as background, so MPICH, unlike say OpenMPI, allocates objects from its own internal object pools, and it assigns them C integer handle values, or assigns integer handle values, whether it's C or Fortran. But literally, we have this type def int MPI request. So I think other, OpenMPI and maybe other communication libraries use pointers for handles. We use integers, and so this is this complicates things a little bit, but it does have some benefits. So you can encode information in handles like this. That's kind of why we like it. So it's eliminates maybe a memory lookup for certain types of objects in MPICH, not necessarily requests, but other things like data types. So it's kind of a nice feature. But the other reason it's likely to stick around is that it's part of our ABI, and we're really ABI sensitive in the MPICH project. So we're unlikely to change this anytime soon. So it was clear that the tagged APIs in the past were not necessarily designed around this mode where the communication library was going to be allocating its own request objects. But the MBX interfaces are a huge improvement on the past APIs. Less so for send. So I think I talked about this last time I gave an update. For tag send MBX, we're still not providing our own requests to the UCX library. I think as one potential solution for this would be to use the MPICH request as the UCX request. We're not doing that because we really like the optimization where UCX doesn't allocate a request at all, because MPICH doesn't have to request or allocate a request at all, and that's a nice optimization for small kind of immediately complete operations. As I noted before, I think I suggested, well, what if we add a flag that tells UCX always return if you can't immediately complete this operation. And then I'll know I'll allocate a request and I'll give you the request and you can use that. This turned out to not work as well as I thought it might in my head when I suggested it. The reason was, I try the operation, it doesn't immediately complete. I allocate my request and then I try again, and the operation does immediately complete. So it was kind of like a it didn't necessarily work as well because I think the code I was writing was expecting the second try not to complete immediately, but then it did, and so it ended up kind of making that code really messy to handle that situation. So anyway, on the send side, things remain mostly the same with the adoption of MBX, which is actually not that big of a deal. It was really the receive side that was mostly problematic. And again, we're not using the ability to provide the request to UCX as maybe we thought we would when we originally looked at these APIs. The major improvement in the MBX interfaces for tag receive is the addition of the user data parameter, because that we just use as a pointer to the MPICH request struct, the underlying struct, not the handle value. And so what this gave us was a way to make the MPICH request available in the completion callback no matter what. Because before we didn't have a way to do that, because the UCX request had, may not have been allocated yet because the UCX completion callback might have executed before we had the chance to associate the UCP request with the MPICH request, then we had to have all this complex handling. Now, because we have that user data parameter that's present in the start of the receive call, then we always have access to the MPICH request at completion time, which significantly simplifies the request handling. So that's really great, and we're happy about that. Active messages, like I said, so now before we used to layer the MPICH generic active messages over the tagged interfaces, but this had some negative performance implications because we were always checking to see if there were generic messages in the queue or in the receive lists. So now we're using the active messages, which kind of are decoupled from the tag receive queues, which eliminates any kind of overhead by having both sharing the same resource. We're still using the NB, so we haven't yet updated to the NBX active message interface. So we're still using the old NB interface, using the whole message flag. It's good. The porting was really straightforward. Eliminated that message matching overhead like I talked about. We do need to copy data for alignment purposes, but again, I saw a PR from Mikhail that may have addressed this for us that we should probably test, but it looks like we can now specify an alignment for incoming active messages. We do want to update to MPICH, the MPICH version of the interfaces, but we need to do some more testing. I think the answer to this question is yes. Does the active message interface support device buffers? But I think we had run into issues in our testing where we saw problems with that. So I think we've seen some fixes come across that may have addressed that. But anyway, that's something that we need to do some more testing on and see if we can upgrade to the newest version of the interface. I'll talk a little bit about multi-threading optimizations we've done inside MPICH. So we have what we call a virtual communication interface, or VCI, that is a kind of an object, a software object inside MPICH. The idea here is we allocate these VCIs and map them to network resources. In the case of UCX, that's a worker. In our implementation, and then threads can use these independent resources in a more scalable fashion rather than trying to share resources and contending for locks and things like that when using them for multiple threads. So there's I put the title of the paper here. And I think Rohit's even on the line, so he can tell you more about it. But this is based on work from a student of ours. Well, he was a student at the time, about how to improve MPI thread performance without going as far as having a thread specific interface for MPI, but using the existing MPI 3.1 interfaces. And this, like I said, mapping thread operations to independent resources in order to get good scalability. So this is kind of the nuts and bolts. We still use a single context, but we do indicate that it's going to be shared by threads using different workers, and then our workers, like I said, MPICH is locking the workers by protecting the workers so that operations are serialized. There will be multiple threads potentially using different workers, but they'll only be using them one thread at a time. So we use the serialized thread mode. And then we do an all-to-all address exchange endpoint creation so every depending on how many workers you have, if you have 2 workers, then you have twice the amount of addresses, endpoint addresses stored, so it is a big resource hog, as we talked about in one of the other talks touched on, though in the context, with context rather than workers. And so I did some performance evaluations of this actually last night, yesterday, using a couple available multi-threaded benchmarks just to show how this is working fairly well. This is using RTEM's multi-threaded communication benchmark. This is point-to-point message rate test with MPI. This is on Intel Xeon platform here, Skylake with ConnectX-6, one process per node. Importantly, we're using COM per thread. So this is how MPICH distributes, communication to the different VCIs internally. By default, it uses different communicators or different windows for RMA, like I'll show later. We also have, planned schemes for distributing work based on, the user, the tag of the message, or potentially the rank. Those are things we want to look at adding. But right now, using a thread per communicator, or communicator per thread is the default way to get kind of isolation amongst threads. So you can see this is pretty good scalability, especially for small messages. You see, almost linear increase as you go to 2 threads and 4 threads here in the message rate test. Similarly with RMA, and this is log scale, so be careful how you read these. But again, this is a latency graph. So we see with small messages, the latency, there's virtually no overhead as you increase the number of threads. Again, we're using this -W option. So this is the LANL RMA multi-threaded performance benchmark. We're doing a window per thread here. So again, we have to isolate threads in some way to kind of make sure they're not contending for resources. But virtually no overhead and small message latency, and in bandwidth, again, we're getting fairly linear scaling as we increase the number of threads. What we're looking at working on in the future. So right now, as I said, we have support for contiguous RMA put-get with MPI, with MPI RMA windows. One thing that we should add, we have it for our libfabric integration, but we don't yet have it for UCX, the support for non-contiguous RMA. And this is, I'm not saying, the UCX doesn't support non-contiguous data types, but what I mean is when we have, a dense data type, then we can, instead of calling up to the generic layer and packing all the data into a buffer and going over the emulation path, we could still use native operations. We just issue multiple per contiguous segment of the dense data. If the data is sparse, then we'll just pack it and again issue a native operation as opposed to what we do today, which is fall back to the generic, the active message based or layered implementation, which is not as performant. Again, I talked about we need the dynamic process management to have a full MPI implementation with MPICH UCX. So we need to test that new address format or implement a workaround for when we can't support it. Native atomics, again, I talked about that, so I won't say anything again. And then what's down here at the bottom, and it's something that we also definitely want to look at as UCX collectives. Prototype this out, evaluate it, assume, we've heard a lot of good things, so we want to get that integrated, and hopefully it's pretty straightforward porting from what we have currently, which is the HCall integration in MPICH. Other odds and ends. So I put this up here last time. I think I talked at the annual meeting, but I be a little more specific about it now. So we run a lot of testing. We do a lot of Jenkins testing with our MPICH UCX integration, both nightly and per pull request. One thing that's been really great for us is the addition of sanitizers into the Jenkins tests. So we are using address sanitizer with MPICH plus UCX, as long as we set these environment variables in order to disable some of the memory hooks that UCX uses by default. So just as a point of note, that address sanitizer does work well with UCX as long as you disable those hooks, which has helped us find leaks and other weird behaviors. We also use undefined behavior sanitizer, which has been great especially for initially discovering that alignment issue with active messages, because as most folks know, on Intel platforms, alignment is not strictly enforced. You can do pretty much anything you want. It just won't, it may not perform very well. But if you are to move to another platform like ARM or Power or something like that, you might get a SIG bus or something and a crash. But luckily, undefined, the UBSAN can find this stuff for you no matter where you're running. And so you can implement a fix for it before you get surprised by a crash on a different system. So that's all I've got. A list of pointers here are the MPICH website, mailing lists, our GitHub where we do all of the MPICH development out in the open. So if you have an issue or you want to fix something, please submit an issue or a PR to us. We'll be happy to take a look. And we also have a Slack channel where we discuss MPICH. There's some NVIDIA Mellanox folks on there already, and we're happy to have more there. Just ping me for an invite. So that's all I've got. Thanks. Any questions? I see one in the chat from Yossi about with the immediate completion. Maybe we're not setting no immediate completion for the second. That's a good point. Yeah, I guess we haven't tried that. I could see if that gives us any benefit. I guess I'm at the reason we're not doing it is I think at that point we've already resigned ourselves to allocating the request, and so we might as well just go through the full completion path. But it's worth a shot. We could see if it does provide any benefit.
Any more questions for Ken?
I was wondering, what was the exact problem with trying with forcing immediate completion first and then second time without it? And if it at the second time it completes immediately, what would be the issue with that?
Yeah, I'd have to dig back in my notes for why that is an issue. Yeah, I guess so if I'm remembering correctly, so we essentially, we have this completion handling that either happens in the completion callback, or it happens after we know the operation is immediately completed, and whether or not we need to. I suppose if we just had a helper function that did that, then it'd be trivial to kind of do it in both places. Mm-hmm. So I think it boiled down to that. But yeah, like I said, I think because once the immediate completion has failed, and we're gonna, like at that point we say we are going to go ahead and allocate the request, and that's expensive. We're taking a lock, we're grabbing something out of the memory pool. We're initializing all the fields. At that point, we might as well just go through the full completion callback path. The immediate completion isn't really going to save. Whatever it saves us is not going to be much, I think, over the request initialization at that point. So I think that's why we kind of resign ourselves. But yeah, it's probably not as much of an issue to do the completion processing in both places, whether you do it after immediate or in the callback. So I'm probably overstating the messiness there.
Right. So because of this, you right now do not use that immediate completion flag at all. You just always create the request.
No, we only create the. So we don't supply force immediate completion, but if the request immediately completes, right? So if we get back null from tag send NBX, then we just return the user a pre-completed request handle. Mm-hmm. If it fails, if we do get back a UCX request, then we go ahead and allocate the MPICH request and associate the two, because one of the things that's improved, at least over initially when we integrated UCX, that send no longer triggers a progress if it allocates a request. So we can confidently say that if we get back a request that it's incomplete, and we can associate the MPICH request with it before the completion callback.
Okay, because that's what I was wondering. So how can you make sure that the callback has not already been called before you do that association? Okay.
Yeah, and that change went in a long time ago, probably like 1.6
Right.
or something. Yeah.
I see. And is this also one of the reasons that you are not using field request and not passing the request to UCX? I mean, you pass MPICH request as the user data, right?
Yeah,
why
we do
not
that in
as
the
the
receive path. We do that in the receive path because we always have a request in the receive path, but in the send path, like I said, we can return this pre-completed request, like statically allocated pre-complete request, which again is a huge savings. You know, it saves all that memory pool allocation and it field, struct initialization. So that's why we don't supply anything to UCX, in the immediate, in case the operation can immediately complete, because it's a big optimization.
Yep. All right. Yep. Thank you.
Thanks.
I just have a short note
Michal.
that regarding the issues with active message alignment and device memory support, it should be already in place in the master or UCX 1.12. So it would be good if you can test it and raise an issue if something not working still.
Sounds good. Yeah, we'll take a look at that.
Okay, thanks.
All right.
Any more questions? Okay. Let's see if we have any more questions. Ken, thank you very much for presenting this. Good stuff.